Hey, thanks for joining me for the second video of section 2.1, the graphs of vector curves. In this video, we're going to do example 2.1.1 and example 2.1.2. So let's go ahead and start with the first of these. And so we have in R2, so in the plane, we're asked to draw the vector curve given by r of t is equal to cos t, 2 sine t. We're asked to then identify the curve and give its equation in xy coordinates. Xy coordinates, which are also called Cartesian coordinates. So let's do this old school. We'll actually start by doing a table of values. So we're going to look at different t values and different r radial vectors, r of t, that they give us. So 0. If I'm plugging 0 into the r vector, so cos of 0, 2 times the sine of 0, so cos of 0 is 1, sine of 0 is 0, which 2 times still gives me 0, so my first vector is the vector 1, 0. So if I give myself a set of axes here in the plane, there's my x-axis and a y-axis here. So x and y. Then my first vector is going from the origin. I'm drawing all my vectors in standard position. There's my first vector, and of course it's going to the point 1, 0. So now we've got trig functions, so let's look at some standard trig values, or pi over 6. The cos of pi over 6 is root 3 over 2. The sine of pi over 6 is 1/2, but then we're multiplying by 2, so 2 times 1/2 gives me 1. Which means my next vector goes up. Let's add maybe a little bit of scale here. If this is 1 on the y-axis and 2, so we're going to root 3 over 2, which is 0.866 approximately, and 1. So somewhere there-ish. And the idea, of course, is that the curve is being drawn out as the vectors move, right? As t increases, the vectors are moving in that direction. So the curve is being drawn out in that direction. If we look at our next value, pi over 4. Cos of pi over 4 is root 2 over 2. Sine of pi over 4 is the same, but I'm multiplying by 2. So we have root 2 over 2 and root 2. So about 0.7-ish and 1.4-ish. So somewhere there-ish. It's a lot of ish. There's our next. And then we have the next standard trig value, pi over 3. Cos of pi over 3 is 1/2. Root 3 over 2 times 2 gives me root 3. So we're looking at 0.5 and 0.7 approximately, so somewhere maybe like that. And the last vector is going to be, or the last one that I'm going to draw anyway, pi over 2, so cos of pi over 2 is 0, sine of pi over 2 is 1, times 2 is 2. So my vector goes up like this. Okay, and I can see maybe I should adjust this guy a little bit because I know what the shape is supposed to be. And we are imagining, again, the curve being drawn out as those vectors sweep through. These being trig functions, we can expect a certain amount of symmetry as we go around the axis. And so I'm just going to fill in by symmetry here what the rest of the curve will look like. And we see that we have an ellipse. And as those radial vectors are spinning around with increasing t, the curve is being drawn out in that direction. So we're being asked to name the curve. It's an ellipse. And the ellipse that has intercepts of 1, 0 and 0, 2 is in Cartesian coordinates x squared plus y squared over 4 is equal to 1. Example 2.1.2. Now we're asked to draw the space curve. So in R3, r of t is, and we'll notice that the x and the y coordinates, the components, are the same. Cos of t and 2 sine of t, and we have z is equal to t. So we're not going to make a table of values for this. We're going to draw this one freehand using the work that we've done in the past example, the previous example. So let's add a set of axes in 3-dimensional space. So there's my x, my y, and my z axis. And I'm going to start in the same position, right? We started up here at the point 1, 0. Well, if I put that, embed that into R3, it's here. The relationship between x and y doesn't change, right? The relationship between x and y doesn't change. So if it were just x and y, we would get the same curve here. But what happens as t increases, instead of following in the same path, z gains t, which means z increases. It gains height. So we're going to get an ellipse that's being spun around as t increases. So let's draw that in blue here. So we get the ellipse, which is kind of stretched out like a spring, like a slinky. You remember that wonderful toy? Maybe you don't. It was a toy when I was a kid. There you go. And so you could call this a spring if you want, but the official name for this kind of curve is a helix, like DNA. DNA is a double helix, so this is a single helix. And because it is based on an ellipse, it's called an elliptical helix. So let me just write you a note about what was happening here, right? The relationship between x and y is the same as in part A. Hence the elliptical shape. And the z component, right, z is equal to t, so z gains height as t increases. So if I wanted to draw in a couple radial vectors, I could draw one sort of here, and imagining that it's spun around, right, it might end up at some later point for a higher value of t there. So this could be sort of r of t0 or t1, maybe, not necessarily our initial value, r of a later value t2. So the direction of the curve is here. So we're imagining the curve being drawn out as the radial vector r of t spins around like that, in that direction. Here's an animation of our elliptical helix being drawn out by a radial vector. So this is the helix that we just graphed ourselves. X is cos t, y is 2 sine t, and z is t, which corresponded in the xy plane to the ellipse here, which is x squared plus y squared over 4 is equal to 1. So you can sort of get a picture, an idea of how this helix, this spring, is oriented in 3-dimensional space. And there's one more thing that I'd like to show you about this helix, and that is that the helix can be drawn on the surface of a cylinder. Now, what cylinder do we think that is? Well, the helix, to be on the surface of the cylinder, must satisfy the equation of the cylinder, Obviously, the helix is a one-dimensional object and the surface is a two-dimensional object, but that cylinder is the cylinder where z is missing. It's parallel to the z-axis. So it is the cylinder x squared plus y squared over 4 is equal to 1. The same equation of the ellipse, if we look at the projection down into the xy plane, is our ellipse. But if we graph it in 3 dimensions with z missing, it is a cylinder parallel to the z-axis, and the elliptical helix, which also satisfies that equation, can be drawn on the surface of that cylinder. So a plane curve and a space curve drawn in these examples. In the next video, we'll take a look at even more examples of graphs of vector curves.